Hey guys, we'll be going over regulation by fructose 2,6-bisphosphate. Regulation by fructose 2,6-bisphosphate is involved in the reversible, rate-limiting step of glycolysis and gluconeogenesis. How does fructose 2,6-bisphosphate fit into the glycolysis pathway? Think of it as a regulation molecule or a side process that can go along with glycolysis or gluconeogenesis. It's created by phosphofructokinase 2, or PFK2, when fructose 6-phosphate is converted to fructose 2,6-bisphosphate. It gets broken down by fructose bisphosphatase 2, this enzyme here, back into fructose 6-phosphate. Fructose bisphosphatase 2 and phosphofructokinase 2 are actually part of the same protein, but respond in opposite ways to phosphorylation by protein kinase A. So just to note, this reaction here in this page is essentially the same reaction as this one that's included in your book. For some reason, I always found it hard to focus on this picture simply because it was horizontal, so I always ended up drawing it vertically to look like this. Maybe it's because I'm used to reaction moving in a top-to-bottom manner, or maybe it's my OCD. Either way, I think you're able to adequately see the side process that fructose 2,6-bisphosphate is a part of a lot better. Okay, so to get you organized, recall that when we eat our lovely broke medical student food, our body can break down glucose to form fructose 6-phosphate and fructose 1,6-bisphosphate via the process of glycolysis. And when our body hasn't eaten in a while or is fasting, gluconeogenesis can be initiated and this reaction can be reversed. So the arrows in the blue depict the fed state and the arrows in the red depict the fasting state. Now let's compare the regulation of fructose 2,6-phosphate in the fed and fasting states. In the fasting state, high glucagon increases the amount of cyclic AMP through a G protein coupled receptor system. This increases the activity of protein kinase A, which phosphorylates fructose bisphosphatase 2. This phosphate group activates fructose bisphosphate 2 and inhibits phosphofructase kinase 2. This means you're going to be converting the side molecule of fructose 2,6-bisphosphatase into fructose 6-phosphate, inhibiting the opposite reaction, which in turn allows gluconeogenesis to proceed to replenish blood glucose levels. And this makes sense if you're in the fasting state, because our body needs glucose. In other words, fructose 2,6-bisphosphate shifts metabolites away from acetyl-CoA production and fat production towards gluconeogenesis. What do you predict would happen in the fed state? Well, in the fed state, high insulin levels decrease the amount of cyclic AMP, therefore decreasing protein kinase A activity. The enzyme fructose bisphosphate 2 will be dephosphorylated, which means that only phosphofructokinase 2 will be active. The body will start converting fructose 6-phosphate into fructose 2,6-bisphosphate, which then activates phosphofructokinase 1, this enzyme right here. Overall, the molecule fructose 2,6-bisphosphate is made to regulate the steps of glycolysis, and keep in mind that phosphofructokinase 1 is the rate-limiting step in glycolysis, and therefore is important to regulate this enzyme more than others. So once fructose 6-phosphate is converted to fructose 2,6-bisphosphate, and the enzyme phosphofructokinase 1 is activated, the body can then initiate the process of glycolysis and break down food. Can you name a few more phosphofructokinase 1 regulators? Great. ATP and citrate inhibit phosphofructokinase 1, while AMP and fructose 2,6-bisphosphate stimulate PFK1 activity. So in summary, during the fasting state, we get an increase in glucagon, which causes an increase in CAMP, an increase in pKa activity, which then stimulates and increases fructose bisphosphase 2 enzyme activity. During the fed state, we have an increase in insulin, which leads to a decrease in CAMP and pKa activity, which in short decreases fructose bisphosphatase 2 enzyme activity and increases phosphofructokinase 2 activity. Your book has a great mnemonic to remember this. Fabian the peasant has to work hard when starving. Lazy spoiled Prince Frederick works only when fed. So fructobisphosphase 2 works during starvation mode, and phosphofructokinase 2 works during fed mode, or the fed state. And that's everything for the regulation by fructose 2,6-bisphosphate. Thanks for watching. If you liked the video, give a thumbs up.